Hello everybody! We have a lot to get through today, so no yapping for this introduction. Let's get started. Okay, well, first of all, a few things have changed. I've worked on this offline, so let me go through what has changed. First of all, you're gonna notice that some code has disappeared. There's no virtual memory initialization here, nor physical memory. That is because we have this new module here called memory that basically takes care of all of that for us. So it basically hosts the heap allocators, vmem for our kernel and permanent allocator, and gives us functions to be able to create an allocator from the heap allocator and stuff like that. So it's our one stop for anything memory related, or so it should be. Right, so you're also going to notice that I've split this, the init methods into three categories. The early init that basically just creates the heap. The init function that does physical memory and virtual memory initialization and sets the kernel vmem to our kernel heap, and then the late init, by which we try to extend our kernel heap to some usable size. And this is pretty much what we had last time. And when we try to run this, so let me just go ahead and do this, and sure, let me try to run this. So last time we had this error here, out of virtual memory. And that was weird because we could never be out of virtual memory. We have 200 petabytes of it or something like that. So yeah, I took a look at vmem. And what we have not done is specify or register enough ranges that we should use. So I went ahead and did that. Let me show you what I did. So I created this little map here of how I think things should be laid out in virtual memory. So let's start from our kernel code, which is this here. We know that our kernel code would start at this address here because we have pretty much specified it semi-randomly, but that's okay. Above our kernel code, we have our environment string, and then above that we have our boot info boot header structure. So this here happens to be at minus 48 megs of virtual memory. Right after our code, we have our quick maps. We have a 2 pages padding, and then we have our quick maps. And then we have, right after those, we have our stack. We know that our stack starts at 0 for CPU 0, and then every CPU gets a page above that one. So if we have 8 CPUs, then he would be at minus 0x8000. And then above that stack, we have our quick map PTE. So this part of the virtual memory grows down, or at least, well, all of them grow down, but this one is allocated from top down, and this one is allocated from the bottom up. So basically we have the first item starting at the lowest page, and then we go up from there. So same goes for this quick map PTE, which means that between this quick map pages here and this quick map PTE pages that we've allocated to set the quick map pages addresses, we can have some free space. Same goes here. This one here is actually the continuation of the stacks. So below the 0, we have some memory that should not be, I think some addresses that should not be allocated, and I think we might have to reflect that here. So this here would not be 0, it would be some address. And I think here would go all the way up to something like, let's go for the first 4 megs of memory. We would want those to be identity mapped, but we don't want those to be in our ranges. So yeah. So let me just leave that here because this map here shows that this is identity map, which is okay. Right, so with this in mind, I actually just went ahead and registered all the ranges. So, oh, actually, I've never talked about what's above the kernel. So I placed the frame buffer 64 megs above the kernel, just in case we want to do double or triple buffering. I think 64 megs would be more than enough for that. So we'd have a frame buffer for 4K with 32-bit colors, plus probably 2 or 3 other buffers of the same size to basically have some double or triple buffering for our graphics pipeline, if we come to that. Here, again, 128 megs above that, I've created the MMIO area, which would be used for mapping devices to memory so that we can access them. I also consider that anything that's, any bar or PCIe bar, stuff like that would go in this area here. That's why it's so big. And then above that, I consider that from the -1 gig mark to minus 256 megs, so that's about 750 megs of virtual memory, would be what we should be using for our kernel. We actually have the higher limit would be something like this, which would be minus, God knows how far this is, but I don't think we are going to need to use all that memory, and trying to keep our resources fairly constrained, just in case we need to port this to some other architecture that doesn't have as lavish virtual memory mappings. Right, so that's what we have done here, and here, of course, I have this final range, which is the this one, the biggest range, commented out. So let me just comment that. So now if we go back here and we try to reallocate or rerun this, we're going to see that now it fails with a different error. So it's not saying out of virtual memory anymore, it's saying out of memory. And the reason for that is, it's very simple, but it's very sad. So if we go to our heap, we try to allocate pages here, or rather we try to extend. Here I've added a few log entries here. So the first one we can see it outputs the current size of our permanent allocator. And then the second number here is the total size. So we are doing fairly okay. We are still far from the 4 megs we've allocated. But this line here, this init, does fail. And it fails with out of memory because the allocator is not able to go through with all the allocations it needs to do. Reason for that is, let's go back here and try to go through a few of these allocated things and see what we get. So buckets are fairly okay. Buckets is just a free list. Free list is just so 2 pointers, which is okay. So we can allocate as many as we want of those, and it should be all right. Node state. This one here is actually fairly big because we allocate a node state count, which would be the number, half the number of nodes we can have in our tree. So for 200 megs, if we allow allocations to go down to just 8 bytes. Actually, I think I've changed a few things here in Heap. Let me see if I can find my buddy allocator types. Okay, so no, I've just put safety to false, and we'll get to that. But the minimum allocatable type is still 1 here. So if we want to go down to 1, that means that we have 200 million nodes at the lower state, and that would basically correspond to the number of nodes that we are going to try to allocate. So that means that for 200 megabytes, we are going to allocate here 200 million bits to track the states for those. So that means that that's 200 divided by 8, that's 25 megs. We only have 4 megs in our permanent allocator, so it's not going to work. And that's with safety off. If we add safety on top of that, and we go to the init for this safety block, so here allocated is allocating the number of nodes, which would be basically a lot more than, so it would be 400 million basically. So we need 50 megs to accommodate all the safety data for just 200 megs of memory to be allocated, which is quite a lot of waste. Same goes for stack traces. We'd probably have quite a lot of them, and these ones here are so stack trace is basically a number of U sizes plus another U size. So num traces plus 1 times num trace types. And given that num traces we have in our config here is 6, so that means 6 plus 1, 7 times 2 is 17, times the number of basically nodes that we are trying to allocate, which is a lot. So safety is for now disabled. Right, so if we go back here and we try to also set our min size to something like 8, here would basically divide the requirement by 8, but let's see if this still works. Yeah, so this one here works, but just barely, because when we try to allocate our stacked traces, we get an out of memory right away, because there's no memory left in our allocators. Yeah, so let's fix that actually. To fix that, I think we are going to go to kernel main, and let's just move this debug init here right after we do our late init. And instead of passing it the permanent allocator, I think we are going to pass it kernel alloc, which we just recently extended. All right, let's try this. There we go. So it looks like it's working. Yeah, I'm just going to do something here. I want to see, just before we panic. So stdlog debug, sure. And I'm going to print the allocator stats. So kernel allocator stats. And we'd have, actually, can we do something like this and do something like, Yeah. Right. So we want total, or rather free mem, and we want that as should probably get some helpers to format strings for us, shouldn't we? Yeah, so free mem is that much, and available mem, sure, is that much. Sure, okay. So this one would be kernel. No, this one would be memory dot kernel heap. Oh, it's not. It's not. It's not public, is it? All right. Let's move this to memory. Should probably go here and do public function. Print stats. Sure. Void, and then here we can just stick this in here. I think we have a logger locally. Yes, we do. Right. So this one here would be kernel heap dot total free memory, and this one here would be kernel heap dot available allocated memory. Wait. Okay. So that means free memory, allocated memory. And let's just add here total mem, just so that we know. And this one here is, well, kernel heap dot total allocated memory plus kernel heap dot total free memory. All right. And let's, of course, call this from our main. So this one would be here. It'd be memory.print stats. No need to try anything. That's okay. Whoops. Clear. Oh. Okay, so let's see here. We have 200 megs of memory, and we have 0 allocated memory. That's not going to work. That is not true. That is not true. This guy here definitely allocates memory. Okay, hold on. Let me try to do something else here. Let me put this above and after that. Okay, let's see here. All right. So we do have a problem. So this guy is initializing. Is that something that we see? Yeah, initializing debug info. We don't see no debug info. Well, so that means that it tried to load them. That means that we go through the allocator. Whoops. And that means that we do allocate things. Yeah, we at least allocate this. Open here does allocations. Okay, that's not good. That's not good. So allocator goes through alloc, which basically does this. And then that does, oh, so we've never actually tracked allocations. Very nice. Very nice. Okay. Self dot track sure, let's just put in what do we put in here? So this one returns a pointer, but we don't have the actual size we try to allocate from it. That's actually pretty bad. How do we get the size from this? You know what? Let's just track the aligned size for now. Sure. Let's just track the aligned size. Yeah, sure. Let's just do something like total free memory minus equals, or let's go for const estimated size is alignment dot forward length. Sure. And then we do estimated size, and then self dot total allocated memory is plus equals estimated size. Sure. Let me just get this down here, and we do this just before we return. Just going to not forget to flip these two here, and then const estimated size is alignment dot forward forward. Let's get this right. Of length, or rather of memory dot length. Sure. Yeah. Actually, I do think that this might be problematic because it's not the memory length that we want to forward, it's the you know what? It's an estimation, so we move. Right, so let's try with this now. Hopefully we get a clearer idea of what we're doing. All right, cool. So we have allocated about 5 megs just for the debug info. It looks like it. Very nice. Cool. Very cool. So now. We still have our. So okay, let me address the other thing that I want to address. Body allocator turns out not a great idea. At least not for a lot of memory. We have allocated 200 megs, and we had to do quite a lot of concessions just to get that to work. So let's see here. Our permanent allocator can at most allocate less than twice that amount, so less than 400 megs. I think we'd cap at about 350. Let's try that. 380. I'm pretty sure this is going to panic with out of memory. Well, it's not panicking, but it's doing something that's not good. Yeah. Something there is not great. Let's try with something else. Let's try with 5 or 350. Okay, so I think we do have a problem in our virtual memory code. Let's get to that vmem. So I think we are mapping memory range to that other physical range, and if we go down here, let's just enable this. We are going to get spammed, but that's okay. All right. Okay, so why does it stop there? Yeah, it feels like we have something that we overwrite or something. So physical address this to virtual address whatever this is. This still should be fairly higher up. We still should not get any virtual address collisions. So what is going on here? Yeah, there's something that's a bit weird going on here. Is it also because we might have... hold on a minute. So I actually also did quite a lot of work on this virtual memory things to make them architecture specific, or at least whatever is architecture specific has been moved to the Arc module. So basically here we have this virtual or platform virtual allocator, which is in Arc memory virtual allocator, and that takes in a virtual memory manager that basically takes the ranges and handles allocations and stuff like that. And this virtual allocator does just platform specific things like calling registers, doing table creation, stuff like that. So yeah, let's see here. Should we probably do something like that? Would be, yeah, sure, why not? And so, yeah, I also did something that I think is fairly okay to do. Is I've moved the types to arc-specific types for v address and p address, as well as their max sizes, so that we can address them. That means that now if we move to something else that has no virtual memory or something, we could lose this struct here and just use a U64 for virtual addressing and stuff like that. Right, so let's try this again with the log. Okay. So, oh, is it because... Oh, I think I see what the problem is. We allocate pages to write to, but we never actually map them. Yeah, so we allocate pages and we write to them, but we never actually map them. And so we assume that these pages here are identity mapped, which I don't think is the case. If we go to UEFI main, yeah, so the limit of the number of pages we've allocated as identity maps is this. So if I change this here, I think we should go a bit further in our allocation here. Yeah, hopefully that's the issue. But if that's the issue, that means that we have something very brittle here in our memory allocation. We are skipping some mapping step. Yeah. All right. So yeah, we get further than that. we try to allocate and now we fail with out of memory. So 350 is too big for our permanent allocator. Let's try something else. Let's go here. What is the maximum size that we can actually allocate? I'm actually going to also remove the few log entries that we've added because we don't need them anymore. So what was that one? So mapping p address. Okay, so that still gives us an out of mem. So there's not many things we can do. Let's go to 80. We know that 200 works. Yeah, 280 is still too big. Let's go for 250. Okay, so 250 barely passes, I think. Let's see how big. No, I think 250 is okay. Might go to something like 260. Okay, no. So it's between 250 and 260 that we hit our limit, which is not great because we expect to run this on a modern machine that can have up to 64 gigs of RAM, or maybe even above that. So to address this problem, I think I'm going to go to roadmap and just add in a new entry here. Slab allocator. Turns out this is not a great idea for fine grain allocations. Yeah, so I'm going to take some time and offline work on a slab allocator. It should be fairly easy. So slab allocation, for those who might not know, is you get a number of pages, contiguous ones, depending on. So you decide on a minimal number of objects that you want. So let's say we want 4 objects per slab minimum. And then you are given a type. So you take the size of type, so SO type, that gives you a size, an object size. You take also alignment constraint. You apply that to the size, you get an aligned size. Then you take that aligned size times the minimum number of objects that you want in your slab. That gives you a number of pages that you need to allocate. You get those pages and then you initialize all those slabs. Let's go for 4. So for example, we have this object here. So let's shade it this way. Let's shade this one this way. And then you'd have this other object here. They're all the same size. I'm just bad at drawing this. And of course here, you'd also have, if you want to go into details, you'd have some waste on your page because you can only fit so many objects of a given size onto n pages. So this waste here, you can probably run an optimization routine on it to try to see if with 2 pages I can fit 4 items with a space of whatever this is. If I take 6 pages, I could probably fit more than 4 items. How does this wasted space here behave? Does it shrink or does it grow? And if 6 pages is not enough, we might go to 8, and then we try to run an optimization routine to basically try to shrink the space to below, I guess, a sort of given limit. Let's say we want to waste less than 1/16th of a page, for example. So if this is our logic, we'd basically just try in a loop number of pages with this size and alignment constraints. We compute number of items that we can have. We see how much wasted space we have, and we try to compare it to this. We divide by 16. We try to compare it to the last one. If it shrinks, then we take the best number of pages. So that's pretty much how it goes. And then since all the objects are the same size, the only thing you need to do is, and obviously here I've left this space here at the top of the first page, because this one here it may contain the header of our slab allocation. So all the metadata can go into this first slice here of the page. Otherwise, you can just allocate the header, the manager, and all other metadata to an external allocator. So maybe our permanent allocator or something like that. But the idea is very simple. You basically get this, do the computation here to see how many pages that you want to get. You can forget about this optimization routine if you want to simplify the problem. The only problem that remains is that how do we find empty items? Because items can be, they are allocated contiguously, but they are not freed contiguously. So you can find yourself with a situation where this item here is allocated, but this one is free, but this one is allocated also, and this next one is probably also allocated, and this other one is free. So what you would need to do is create a sort of free list that basically is stored in the metadata and points to the first free entry. And in the first free entry, you'd basically cast that to a pointer type, and you write on it the address to the next free item, in which you write the address onto the next item. So allocating an object would just be, get me the free list, what is the pointer on it, that's this pointer here, take its value, set it to the free list, and then return the address of that object as allocated. And when you free an object, you just basically, wherever it should be, you just place it on the top of the list. So if this one is free, we take the pointer to the free list, we write it there, and then we point the free list to that object, so that it becomes the first one to be allocated next time. Yeah, so fairly easy. I think I'm going to take that offline and probably just show the work on that once the bases are set. But for now, let's just finish up with our heap allocator. So let's go here, try to do something like, so pub_const, what we need is a page allocator. Yeah, right. So page allocator. This one here is of type, std_mem allocator, and we should probably just initialize this with pointer is so I'm thinking yeah, we should probably not do it like that. Should probably do public function page allocator or something like this. That returns a std_mem allocator, and this one here returns kernel heap dot page allocator, since we already have that in here. So public function page allocator self is pointer self, of course, that mem allocator is our return type, and here we return a. So pointer is self. Let's try to move this along. vtable is this thing here. Let me just do that. So alloc is alloc page sure. Free is free pages, and of course I'm just going to take these two here because we are not doing resizes or remaps. I'm pretty okay with that. So alloc pages takes in a pointer, which is an any opaque pointer, takes in a length, which is a usize, I think, and then takes in an alignment, which is a stdmem alignment, and returns, I believe, a something like this of U8, with, of course, I think we just have this as our, yeah, there's no alignment put on those. So this one here would like to, you know what, I'm just going to go ahead and do this because I just don't care. Whoops, can I just find my way? Yep. So self dot allocate pages takes in a count, so length. All right, so let's go here. Thinking, yeah, so let's go for page count is len div exact. Div exact would panic. I don't want to panic. I just want to So we want to return if not sure what the best way to do this is, but let's do if length mod arc constants default page size is different than 0, then we return error. Oh, we can't error from this. No, actually, this is not good. We should probably just... We know that we are going to get the alignment, so we should probably just align that to page. We could actually disregard the alignment because we know that our alignment will surely be a page. So if alignment compare, sure. Oh, we need to pass it an operator. I'm not into that. Actually, no, hold on. I'll be okay, I think. If not equal, and of course the other one is of arc, no, from byte units, arc constants, default page size, sure. If it's not equal to that, then we return null, because if the alignment is not greater than or equal, but that's not really what we want. We want this to be multiple of pages. Either a page aligned or multiple of pages aligned. So basically aligned to 2 pages or 4 pages boundaries, which should not pose any problem for our current architecture, but it could differ for another one, so we are not going to take that for granted. Yeah, so let's actually try to make this work. How do we go about this? All right, you know what? For now, let's just move on and we'll see where we get to that. So page count would be, so length, or rather, alignment dot forward length divided by our constants default page size. Right, so this one here gets us page count, and then we get our struct here. Sure. You know what? We're going to ask for them to be zeroed. Whoops. And here we catch and return null. Since this one can error, I think. Yes, it can. Yeah. Okay. We might also try to adapt the return types because this one here has the alignment. So, no, that should be okay. So that's for alloc pages. So here, let's go for free pages. This one here would take what? A pointer, of course, which is any opaque. Takes in memory, which is a slice of U8, I believe, and then takes in alignment, which is a mem alignment, and returns void, I think. Is it what we have? And of course, it takes in both take in return address, which we've neglected here. So red address, which is a U size, which we are just going to forget about for now. So red, why am I doing this? U size, sure. So here we are going to do pretty much the same thing. Just copy this over here. Instead of having length, we have memory.length. Okay. So now we go here and do public function free pages takes in self pointer to one self, just this for now. Probably, yeah, let's go for void and we'll try to do. So we have we are going to need to go through these operations in reverse, I think. So let's try to also take arguments. We'll also need to take in memory. So we are going to take memory, which would be a slice of align our constants default page size U8. Sure. And then we take arguments, and these arguments would be a struct that has committed, sure, is boolean equals to false. And we'd also do something like poison, which is a boolean, and this would be also equal to false. And I think poison would do pretty much the same as we did here. So if safety is enabled, we are going to write a known value to a freed page, so that if someone anyone tries to access that page, they get garbage values, and we know that we have a double or use after free error, which is very important for our kernel to have, because otherwise we are just going to be blind. Right, so let's get these going in reverse, I think. So here we probably don't need this. Allocate pointer, we don't really need this either. So here we are going to actually invert those. So if args.poison, and then this becomes, this is a no op, I think. Yep. So let's do if constants.safety, and sure, that lets us make this easier to work with. So here we go memory. Now we need count. We are assuming that memory is the actual full slice, so let's just use memory. Yep. And here what I'm going to do is I am going to just flip this. I'm going to go 99887766, and then we go so FFEE DDCC. Sure. Just so that we know that this is our poison, and this is our basically 0 poison. This is the allocation poison, and this is the free poison, basically. Right, so now that we have probably poisoned this thing here, we are going to go ahead and so we need to do things in order. We first need to free our physical memory. So we are going to first try pmem.free pages, and here we are going to create. So I guess start is just memory, or rather pointer from pointer memory dot pointer. Length would be memory dot length times or just memory dot length actually, and type. Well, this one here I think we can just leave for as empty. What's the default type on this? It doesn't have a one. It doesn't have one, so we probably go for type is free. Sure. Does this fail? It doesn't fail, so we can probably get rid of this. Right, so now we have freed the memory. We should do two things in succession. I think we are going to, first of all, I think I should have mapped or unmapped this first. So try self.vert alloc dot map yeah. The more I think about this, the more I think we are going to need a public function unmap that basically takes itself as a virtual allocator. Oh, I actually also moved vmem to virtual allocator. Sound less or more convincing that way. So vert mem range, and that's pretty much all it takes, and it does it should not. Yeah, I think it should not error. I think it should not error. So I guess we are going to need this. Now, we do this, and we do, so this one would be 0. Unmapping. Yeah, sure. We can probably get rid of this. And we can get rid of this also. Nice. So physical address goes. Virtual physical address here would be 0. Flags would be at bitcast of 0. And args, what are args? Args, I think, give the type or something. Hold on, let me try to find what args are. Force. Should we force the unmapping? Yeah, I think we should. Whoops, force is true. Right, and we don't need this one. Cool. So let's go back to heap, unmap, and here we just need to create a virtual range, which we are actually going to need to reuse. So let's create it here. So const vrange is, so v vert mem range goes with start, I think, and this one here is at bitcast of well, this is kind of bad. Thankfully, we've called that here. So okay, so this one is memory.pointer. Yeah, and this one is length. This one would be memory.length. Sure. Type, we don't really care about that one, I think, in vert mem range. Hold on. vmem.vertmem range, does that work? Yeah, so that one is null. So first of all, this one here is not correct. This one here becomes vrange.length, and this one here becomes, I think we can just get rid of all of this and do something like vrange. Hold on a minute. We are going to need to convert a virtual range to its physical address. So is it virtual arrays.start.get address? Doesn't we have that? The address backstruct. Oh, it's over here. It's in page mapping that we have that. Okay. Right. So back to vmem we go, and we add public function vert to phys takes in self. Sure, why not? Virtual allocator takes in a v address, type v adder, I guess, and returns a p adder. Okay, I guess p address is not defined, so that that would be something like memory arg.memory.p adder, and this one here is defined because we've copied it to, yeah, cool. Cool. So what this should do is, I think we can just go ahead and copy that from here. Yeah, pretty much. So here, instead of flags, I'm just going to do bitcast of 0 because so this one calls get or create, and since we are just doing an M mapping, we would like to just try to get it, and if we don't find it, we should basically just error out. So now that I think about this, can't we do something slightly should we add here a Boolean? So let's add args. This would be a struct. Create if missing as a Boolean would be true. There we go. And this would feed this one, create if missing with a Boolean. So if it's not present and not create if missing, no. So if it's not present, if not create if missing, return error missing page mapping. Otherwise, we go through our merry way. Cool. So this one here should just work. Okay. So what we do here? Arg is not used. Very nice. So args.create if missing, and we should probably do that everywhere here. So we have 3 of those. It's cool. That's all right. And now if we go back to vmem, here we should probably do flag 0 and so this one here needs args will probably create the same as the other one. Create if missing Boolean. Defaults to true, I think. And this means that this one here returns create if missing is args create if missing. Sure. Okay, so this one here, create if missing is false. Set the flags to whatever we want those to be, and we get the entry, and here we return entry.get address. Of course, entry.get address here should probably not be of the address size. It should be the physical address of that. So that would be p address size, of course. Whoops, p address size. Okay. So that means that here we do p address size, and that should all work. Sure. Hold on a minute. We should probably just make this p address, I think. yeah, I don't get why we need to make it p-address size. Whoops, p-address. That should be okay. Now that we have that, we should also look for any use of this function here and just do that in there. That's fine, that's fine, that's fine. So we have 4 of those. We've covered all of them. Cool. Now, going back to memory. No, not memory, heap. Right, so this here takes vrange. Sure. Does it error? Does this error? It does. So, oh, we have catch unreachable in there. Sure, that's fine. That's very okay. So now we have that. We have unmapped the pages. We have freed the physical pages. So now let's free the virtual pages. So self.vert alloc.free range. And this takes in a pointer and a count. Yeah, no. I'm sorry, I'm over this. So vrange is vert mem range. We don't need those, so let me just do whoops. And this one is vrange. Sure. We don't have that implemented yet, but soon TM. So vrange here also. What are these? So this one is type, and I think we can just do this. Because I think vert alloc here type is null. Cool. Cool. So let's think through this. We first unmap the pages so that anyone that tries to access them gets a page fault. And we can cap that. Then we free the physical pages so that we know that we have the correct... it's very good, but we still need to finish this. So self dot, let's call this const phys or p address is self dot vert alloc dot vert to phys with a vrange dot start, and this would be a p address. Yep. Cool. Very nice. So we free the pages so that we know that the memory itself is being freed, and then we free the actual virtual allocation that we have underneath. So yeah, I think we've done the correct steps there. Cool. Let's see here if we're missing anything. I don't think we do, but let's go ahead and build this. Should probably have a few errors. Oh, I think we are going to need to use it before we get the errors. So page allocator here, it's not happy because, sure, common case. Do we, you know what? This is actually a good idea. So page allocator is heap dot page allocator. So let me see here. So do we have hold on a minute. Oh, this one takes a pointer to self. So yeah, I think there's no way we could do this. So probably do it like this. Remove this. The only problem is this would be so I'm not sure when this would be set, it would be initialized fairly early on, and we want that to be actually initialized after this early init. So here's what we're gonna do. Add const cast of page allocator, and we are going to get var page allocator is that shadow, so page alloc, sure. And then we do page alloc is kernel heap.page allocator. Sure. That means that here we can go ahead and do undefined find. We can type that, and we can set the type of this to set mem allocator. Sure. Not sure if that works, but we're going to see. Is it going to complain? Expect pointer type found mem allocator. Yeah, sure. Okay. So the pointer goes inside. Not sure why I put it outside, but sure, why not? Expect type mem allocator, but found. Oh yeah, of course. This should be that. Now, what is the problem with this? Of course, this now is a pointer, so just make that const. So that's fine, I think. Now, if we go to heap 212, I think value of type is ignored. No, return that shit. All right. 218 expected type of. Oh. So this one takes memory now. Okay. It's actually fairly nice. Yep, that's actually pretty nice. I'm pretty sure it's going to complain about the alignment requirement there. Unused function parameter. What's that? 215. Of course. Can throw that away. Now, 217 expect type, yeah. So I think I'm just going for now to do line cast. This is fairly dangerous, but we are only going to know how bad this is once we implement 3 pages. So for now, we're okay with that. No field named zeros or zero instruct 3 pages.struct. So what is going on here? What did we put in here? Oh, it's called poison. Sure. All right, let's see now. Vert mem range is not marked as public. 119, and I think that's in memory here. No, that should be in vmem here. Vert mem range, that should be public. I'm okay with that. Error cannot bitcast from pointer. Oh, I see. So heap 119. Right, so this one here is a v address. This one here is a pointer, so we need to do int from pointer first. And that would make it like us more. Okay. Expected error union type found void. This doesn't fail. This goes. All right. Expected union type found void. Again for 3 pages. Does this not fail? No. Does that not fail? It doesn't. So this one doesn't fail. And that means that, yeah, in 217 we need to get rid of that catch statement that we have. Okay, that should be good. Cannot bitcast from... Okay, well, this is some of the worst design decisions ever. The fact that comp time ints do not autocast to whatever. So for 26. All right, so let's go with this again. And of course we forget this. So, and I'm not even sure what flags are getting cast from. Mmap flags U64, that's okay. And I guess we have the same here, where we need to do this absolutely horrible thing. Yep. All right. Expected type U64 found whatever that is in get page table entry. Get page table entry. Where is that? vmem 431. Hold on. That's the address. All right. Again, expected dot error union set. Oh, I see. This should not fail, like ever. Oh, it could fail actually. No. No. I don't think that's a good API. Let's do catch unreachable. We want to catch problems, but we don't want to impose a try everywhere. We want to convert a virtual to physical address. Okay, so still doing okay for now, but let's go to our main. So kernel main, sure, and go somewhere down here and do memory dot page allocator. Let's call this const page alloc. Sure, and then we can go ahead and do page alloc dot alloc. Yeah, I'm not convinced that stdmem allocator is the best API for this page allocator. I want to allocate a number of pages. I should know the number of pages I want. I'm actually curious to see how std heap page allocator is defined actually. Okay, so let's go through some of these. If we have if in root.os we have heap, or we have heap.page allocator, we call that. Okay, so what's type for that? Or yeah, maybe it should also be an allocator. Otherwise, we are going to go through this and do page allocator.vtable. Right, so let's see how this goes. So if, okay, minus page size, that's fine. Okay, so this one is very OS specific. This is for Windows, and I'm guessing that here we are going to call mmap for, yeah, POSIX mmap. All right. Okay, well, not really sold. Not really sold. So to rewrite this, I'm going to do that when we get time. So let's try to actually alloc, or row alloc. Let's go for 10 times arc constants dot default page size. Sure. This returns const allocated is whoopsie. Of course, let's do this. Rather page alloc dot row free actually, I'm not sure why I did this. We should probably go ahead and do create. No, alloc would be fine actually. So this one needs a try here. This one here just wants to know the type. So the type I'm going to create is actually this. Yeah, let's do something like so arc constants default page size u8. Sure. And here we're just going to make 10 of those. Sure. So this one is free, of allocated. Sure. And then we should probably do something fun like stdlog.info allocated pages at 0x, something with length, something like this. All right, let's see here. We want allocated dot pointer and probably allocated dot length. Yeah, sure. So what is its problem? We have to allocate its to. That's an easy problem to fix. There we go. So now we should have some extra problems. Invalid type given. Oh, of course. int from pointer. Sure. Okay. Oh, right. Ooh, out of memory. That's not good. That is not good. So we asked for 10 pages. Right, let's go through memory allocator, page memory allocator, and then we go to allocate pages, add log.debug, allocating page, and we do size. Sure. Something like length. Is that how it's called? Yep. Let's also do free in page. Free in page. Actually, I want this to be. Let's do int from pointer of memory.pointer. This one, let's just add this. All right. So what do we have here? Oh, wow. Hold on a minute. We've never even gotten to... What is going on here? Page alloc, whatever that type is, and bytes from that. Right, hold on, let me add something here. So instead log info page allocator test. Sure. Yeah, let's do something like this. Okay, so we get straight away, we get a out of memory. How is that even possible? This one is page allocator. Hold on, let me try something else. So instead.log.debug, do some come on, any, and then we do page alloc. Let's see if it's not correctly initialized or something. Oh, maybe I should have. Let's do something like. Yeah, probably not here, but let's do it somewhere here. Sure. All right, let's see. So where do we initialize those things? It should be fairly early, I think. Yeah. So I guess this one is before. Okay. And this one is after. Okay, so we surely have a problem there. All right, I'm over this. I'm going to go back to how this should have been from the start. So public function page allocator, then allocator, and then we do return kernel heap dot page allocator. Should probably rename this since allocator. Yeah. Cool. So we should probably go here, do page allocator, and try again. Okay. Okay. So here at least we try to move forward. So we try to allocate this page here. No, this is the size of the number of pages we try to allocate. And we try to allocate those from this here to this size, or this addresses here. And it happens that we've overwritten something. Okay. Well, at least our allocator works. So if we try to jack up this number here to avoid any space that might be too small, yeah, I guess that's still not enough. So let's go maybe even further. Let's try to allocate a bit more. Okay, so we probably have some kind of weird thing. Right, so it happens in vmem 395, which is a map page. Right. And that is because we try to but hold on, how come we are into this entry here? Why is this entry mapped? Hold on, if address is the same address, or we force it, then we do that. Otherwise, we existing entry with address. Yeah, sure, let's just see what the address that's been there. Oh, shoot. Let's do this. Yeah, let's just change this to error and we could be on our way. Okay, so what we had there is this. Okay, so I think I see what the problem is. Okay. So we are going to go up here Yeah, so this one is done. This one is done, but not fully. So yeah, so go through the physical map and keep the mapping, the identity mapping for every reserved range. I'm not sure if we need every reserved range, but for any range we could not reclaim on startup. So I think that these addresses here, if we go up, they might. Do we print the physical? Yeah, we do. Pages range here. So if we go to C, what was it? The address that caused the issue. So CE8000. So that would be in CE8000. No. It's marked as free. It should be somewhere here. So why is that allocated? Rather, let's go through this in reverse. Let's take a look at the virtual memory that we try to write this page to. And that's so FCC FD 8000 or FCCBE 8000. And let's take a look at our virtual memory ranges. So hold on, let me try this again. So yeah, so 8000, and then we have CCBE on the lower word. So lower word would be this. So FCCBE, this would not be that. Yeah, so it should be in this region here. So why is this region have things that are allocated already? That's weird. Hold on a minute. So this one here has been mapped to FCC. Okay, so all the way down to FD9. Okay, that's okay, I think. Yeah, no, I'm not sure. I see what the problem is. So let's go back to our main and we'll try to do something else. Hold on a minute. Just before we allocate this, I'm going to call memory dot. Oh, that's not cool. That's not cool. So public function print virtual ranges. Sure. This would call kernel kernel vmem dot. Hold on, we could probably access that. Kernel vmem, yeah, sure. Dot print ranges. Okay, so let's go back to memory and get rid of this. Right, so I just want to see the ranges before they get allocated. Okay, so let's take a look at our free virtual range. So here we have FCC 8000. So I'm expecting this virtual range we try to allocate here to start at here. Why did we not get something that starts here? Now, that's the question we need to answer. Okay, well, let's go back then. So allocating pages, memory allocator, page allocator, this goes to here, and then we go here, and then we go here. Very nice. Vert allocator, we get a virtual range. So how does this one work? We get type, and then here we should probably, yeah, let's try to add log.debug. Or rather, allocating vrange with size with the pages. Sure, that's length, I guess. Count. Okay. Nice. So here we get the list from the type, and otherwise we get the free type. So we should probably do something like this, pages from, whoops, and this would be type. Right. So we should probably be over here. And no, you know what? Let's first do this. Log.debug considering range. I think we should have a formatter for that. Range. Yes, of course. Range fits, removing, yeah, we don't need this, and larger resizing. Right, let's not get too lost in the details here. Let's just try to get on with this. Okay. Nice. Let's get this out of the way. Let's make this bigger, and let's see. So here's the problem. Why? Hold on a minute. We want to allocate 1,000 pages. So 1,000 times 2x 1,000. Yeah, we need that in hex. So calc and go 1,000 times 496. Whoops, almost there. So that's 3E8000. So this number here is correct. So why is this guy trying to allocate? Oh, it's number of pages. Wait, no. Okay, so this one here is wrong then. Allocating pages. Okay. Allocating pages. Yep, this is wrong. Page count. Okay. That's not the problem, that's just a formatting issue or just a display issue. Right, so allocating pages 3E8. So that's the number of pages. Wait, hold on. Yeah, so that's 1000. So why is this guy trying to allocate 1000 pages? Oh, because, okay, again, this one is hex, the other one is not. So probably let's try to make this hurtless. Okay, all right, so now we see the same things here, considering the range, this very first one. So FCC, rather no, so it would be CC 80 and 30, so CC 80 and 4 zeros after that. Cool. So this range here should fit. It should definitely fit. And okay, I see what the problem is. Instead of taking the first part of the range that we just resized, we take the part of the range that we haven't resized. Very nice. That's cool. Okay, so this one here would not be this. This one here would be like this. All right. Let's try this again. Okay, this time it works perfectly, since now we allocate, or we use the range that's been allocated to us. Right, perfect, perfect, perfect. So now we do have allocate pages. We get to the end of our main. Cool. So that's it for our heap allocator, or general purpose heap allocator. We still need a free. I'm gonna do that offline, I think. That should be fairly straightforward. I think I've never talked about changes I've made to virtual memory allocation, just to simplify that. I got rid of, actually I'm not sure I got totally rid of it, but hold on a minute. So yeah, I still have them here just as a temporary solution so that everything does not break. But what I did is I created this memory map here, which is an array of lists. Each array is indexed by a type. So I have the types here. We already had them, so I just put them to use, and we initialize the memory map here. And when we try to do an allocation or a free, now it's fairly simple, because what we do is we get the type in args. We just need to select the range list with the type, and the logic itself is fairly straightforward, which is why we had bugs like, or rather, let's say, which is why we could find bugs like we just did fairly quickly. Yeah, so this is for the allocation. The free would take 5 minutes. We just need to call this function that I've created here. It's called add range. I think it's called reserve range. Not sure why I call it reserve range, but what it does is it can take a range from a source and put it into a destination. So we can move ranges between types this way. And what we can do for free is basically just tell it to take a range that does not exist from somewhere and then put it into free. And if the range does not exist, it just creates it. So that would be somewhere over here. And this calls register range that basically creates it into the correct list. So this simplification actually made life a lot easier when working with virtual memory. Right, so that's for that. We still have, I guess, this slab allocator here. It should be a replacement for our body allocator. Actually, I think that our body allocator should become our page allocator, because I think we can, let's actually bring forth the calculator here, and let's say that, for example, we want to have 64 gigs of RAM. Let's go for sure 64 gigs of RAM. And let's go back to our body, and let's go through the allocation. Let's forget for now the safety things. Let's just go through the buckets and node states that we are going to need. So if we set the minimal allocation size to 1 page, it means that we divide this by the size of 1 page and get 16 million nodes at the maximum level, or at the minimum order. We get 16 million pages. So that means that we get 16 megabytes in this node state. So 16 million bits, which if we divide that by 8, we get about 2 megabytes to index 64 gigs of RAM, of pages of RAM. So that's a very nice trade-off, I think. Because if we consider fragmentation and the current memory allocation scheme that we have, with 64 gigs of RAM, we could go through our free list for a while before finding a page or a set of pages that can be allocated for any given size. So I think body allocator would be a very nice replacement. It would also be a drop-in replacement for page allocation. So that's a good idea. It wasn't a waste of time to work on that. So this one should become our page allocator as soon as our slab allocator is online. This one here would basically allow us to create caches for object types. So this is something that's fairly this is what the Linux kernel does also. It has a lot of has a slab allocation scheme, and for any type of objects that the kernel uses often, it creates a slab for that type so that we can allocate that fairly easily. It does a few clever things to align stuff to cache lines and whatnot, but I'm not sure we are going to go there just yet. But yeah, once we get our slab allocator, once that's online, we are going to hook things up. I think it should be a fairly easy drop-in for the general purpose heap allocator. The slab allocator, or rather the thing that will manage slabs, will have the same properties that we want. So it will be extensible. It can allocate more and more pages, create more and more slabs as it needs memory. So it would fit perfectly with how we designed our heap allocator. I guess that's pretty much it for this one. So next time, I think we are going to start working on SMP. Or, yeah, we are going to start working on SMP. So let's bring that here. And we have quite a few topics for SMP, so that would be very fun. Well, that was pretty much it for this one. It was probably not the most exciting stuff to work on, but it's very foundational for what we try to do next. This will set us on good trajectory to achieve what we are trying to do. As always, if you've liked this video, hit like and subscribe. And if you have remarks, comments, or you just want to say hi, leave them in the comments below. I see you, and I'll see you next time. Fucking out.